All right, hello everyone, and welcome to chapter 12, which is all about enzyme kinetics, inhibition, and control. And we're going to start out with this first video in chapter 12, which is going to be discussing reaction kinetics. So, like I mentioned, this first video is about reaction kinetics. So to break that down a little bit, we're going to start by defining and measuring reaction rates. We're going to talk a little bit more about Michaelis-Menten kinetics. And then we're going to end off by starting to interpret some kinetic parameters. In some of the other videos, we're going to talk more about enzyme inhibition and control of enzyme activity. So first of all, let's start by simply defining what is kinetics. And before you continue with this video, I'd actually like you to pause for a moment and think to yourself about what kinetics means. So hopefully you've given it some thought now, and let's go on to define kinetics. So very simply, kinetics is measuring the rate of a reaction or the speed of a reaction, which, to break that down even further, is really essentially just saying how quickly reactants are being used up and how quickly products are being produced over the course of a reaction. And so that's what kinetics is. Something also very important to keep in mind is what kinetics is not, right? So kinetics is not about whether or not the reaction is spontaneous. To know whether a reaction is spontaneous or not, we can use the Gibbs free energy, which we discussed in chapter 1. Kinetics is also not about whether or not there are more reactants or products when the reaction reaches equilibrium. This is related to the equilibrium constant as well as spontaneity, and is not affected by kinetics. These two things that I just said kinetics is not are thermodynamic properties of a reaction. And like we just mentioned, kinetics really is just referring to the speed of that reaction. So let's go into how we might measure the speed of a reaction. So one of these sort of methods of looking at reaction rates is something we've actually discussed a little bit previously, which is the activity assay. And in particular, in previous chapters, we discussed the LDH activity assay. So LDH is an enzyme that catalyzes this reaction that you see here, which is NADH plus pyruvate. It's converted to NAD plus and lactate. And so during the course of the activity assay, we measure the depletion of NADH, which is the reactant in this reaction. LDH absorbs strongly at 340 nanometers, and so we measure the decrease in the absorbance at 340 nanometers as NADH gets depleted over the course of this reaction. And as LDH is the enzyme that catalyzes this reaction, the more LDH that you have, the faster the reaction is going to progress. And we talked also about how during the activity assay, we can use the slope of this line that we can see at the very beginning of the curve as the reaction is beginning, as NADH is depleting, which is telling us more about that initial rate of that reaction. So another way we can measure reaction rates is through an assay called the MTT assay, which is a measure of cellular viability. The MTT assay is a colorimetric assay that looks at the conversion of a compound called MTT into another compound called formazan. And formazan is highly colored, as you can see from this picture at the bottom of the slide here. And so the way MTT gets converted into formazan is through processing by this enzyme called mitochondrial reductase. And so the more conversion of MTT to formazan is a measurement essentially of the metabolic activity of the cell. So the more metabolic activity you have, the more color change that you see during this MTT assay. So let's talk more about how enzymes work to increase those reaction rates as compared to an uncatalyzed reaction. So on this graph we see here on the x-axis we have time, and on the y-axis we have the formation of product. So we can see in this uncatalyzed reaction line we see down here is relatively linear, and this reaction does progress very slowly, right, in the initial part of the reaction. And then eventually, after this break in the graph, as we progress from seconds to hours, this uncatalyzed reaction eventually will reach equilibrium at this high point where you have more formation of product. And this is in comparison to the pink line here, which is the catalyzed reaction using an enzyme. This reaction progresses a lot quicker because, as you can see, you have much more formation of product earlier on in the reaction, sort of during the part that's measured in seconds. But eventually, once you let either reaction go on long enough, whether it's catalyzed or uncatalyzed, both reactions will reach the same equilibrium, right? Where we have the same formation of product. It's simply that enzymes increase how the speed, right? How fast that happens for you to get to that product formation. So let's start to break that down even more. So the kinetics, enzyme kinetics, involves multiple steps. And so this graph should look a little bit familiar from the last chapter. But overall, we have a few different steps. So the initial step we have where the enzyme is binding to the substrate. So E is enzyme, S is substrate, right? So if we look at this graph on the right here, we have the initial part of the reaction where we have enzyme and substrate are separate. Once the substrate is bound by the enzyme, a complex is formed called the ES complex or the enzyme substrate complex. After that, the enzyme helps to convert the substrate into the product, forming this enzyme product complex. And then finally, the product is released from the enzyme at the end of this reaction. And so let's break down each of those steps. So first we'll start with the enzyme binding the substrate, forming this ES complex. And that's shown in also on the top here in this reaction. So enzyme is binding to substrate, it's forming the ES complex. This step happens really, really fast. Enzymes really like binding their substrates. And so this is very fast, and you can think of it almost as an equilibrium, where enzyme is binding to the substrate, you form the ES complex, substrate can leave the enzyme, separating out from separating it and forming free enzyme again, but then as soon as that happens, as soon as the substrate leaves the enzyme, you have almost immediately the, as long as there's substrate available, substrate will then just bind to the enzyme again. And so you can really think of the ES complex as being at a constant concentration, at this steady state where substrate, as long as substrate is present, it's going to want to bind to that enzyme, and if substrate leaves, another substrate is going to bind to that enzyme. However, you can think of this equilibrium as proceeding both forward and backwards, right? And each direction is going to have a rate constant, where the forward reaction of enzyme and substrate coming together to form the enzyme substrate complex is K1. And the reverse reaction where the enzyme substrate complex separates into the enzyme and the substrate individually is going to have the rate constant K minus 1. But overall, we don't consider those rate constants as being as important as some of the other ones because, like we mentioned, this is happening extremely fast, and you can think of the enzyme substrate complex as being at a constant concentration. So what's more interesting or maybe important to us here is this next step where the substrate is converted into product with the help of the enzyme. So, and this can involve one transition state, or it can involve several transition states and intermediates in between the substrate, between where you have the enzyme substrate complex formed and it turns into the enzyme product complex. And this is really the rate limiting step, the step where the enzyme substrate complex the substrate is being formed into the product. And this step has the rate constant K2. Once you have reached this point where the substrate has been converted to product, we're down here again in our reaction graph, and we still have one more step where the product has to be released from the enzyme so that the enzyme is free to then bind a new substrate, right? But again, this happens very, very fast, and it happens so fast that it's not even really given its own rate constant. So really the important step that we usually are considering when we think about enzyme kinetics is really this step where the substrate is converted into the product with that rate constant K2. So another way we can look at this is with this other diagram that's showing time on the x-axis and concentration on the y-axis. We're still looking at that same reaction where a substrate is binding to an enzyme and that enzyme is helping to catalyze this reaction where the substrate is being formed into a product. But here we have some other things we have to consider. So if we look over here, we have the amount of enzyme. And so the total amount of enzyme is shown here as E sub t. And that's a constant level. And so the total amount of enzyme is defined as the sum of the free enzyme that's available plus the amount of enzyme substrate complex. And you can see that, like we mentioned, over the course of the reaction, the level of enzyme substrate complex is fairly constant over the rate of the over the course of the reaction, and the concentration of free enzyme is also fairly constant. And when you add those two things together, you get the total enzyme that's present. And so the other two things that we see on this graph are the amount of substrate. So we have the initial amount of substrate, which is very high, and over the course of this reaction, the concentration of substrate decreases at the same time that the concentration of product increases. And so we can think of this reaction as happening at a fairly steady rate, but you can see that there is some variability. So at the end of the reaction, it sort of starts to level off, where our product formation starts to slow down a little bit, and our use of the substrate also starts to slow down a little bit at the end of that reaction. So, and that's partially because finally, at the end of the reaction, it's going to reach equilibrium, right? And so, again, it's any spontaneous reaction is always going to reach its equilibrium, whether it's catalyzed or uncatalyzed, just like we saw with this graph that we discussed a few slides ago. So ultimately, the enzyme catalyzed reaction is going to reach equilibrium faster, but the uncatalyzed reaction will also eventually get there, and they eventually both meet at this point where there's all this formation of product. So how else can we affect the reaction rate, or what items do affect the reaction rate? One really important consideration into thinking about the rate of the reaction is the concentration of substrate, how much substrate is available. And so as you increase the concentration of the substrate, that's going to also increase the rate of the reaction. Because more substrate is available, it's going to be able to form more enzyme-substrate complex, and ultimately more product is going to be formed more quickly. And we see an example of this in this graph here, where the time of the reaction proceeding is shown on the x-axis, formation of product is shown on the y-axis, and we have these 4 different concentrations of substrate, where S1 is the low concentration of substrate, and it increases up until we reach S4, which is a high concentration of substrate. And the rate of the reaction is essentially the slope of this line, just like we saw sort of flipped over from that activity assay that we discussed earlier, where the slope of the line of product formation over time is just the V naught, right, the initial rate of that reaction. And so for our low concentration of substrate, our S1, that rate of reaction is fairly linear. It's also a fairly small slope. But as we increase the concentration of substrate, that reaction is going to proceed faster, and it's going to go from a linear into a more hyperbolic state, where the initial reaction proceeds very quickly, and it levels off over time as the substrate begins to be used up. And so what can we learn from the V naught, which is that initial reaction rate? So first of all, just as a reminder of the definition of V naught, it's that initial rate of reaction, and that's before any of the substrate is converted into product. And we can measure it as the initial slope as we measure that reaction of the formation of product over time. And V naught, like we mentioned, depends on how much substrate is available, and it also depends on how much enzyme is available. So either substrate or enzyme can sort of limit this reaction rate, or they can help to increase this reaction rate. And so eventually, a reaction can theoretically reach this maximum rate. And this is going to happen when all of the active sites in the available enzyme are saturated. And this is the fastest the reaction can possibly go, because all of the enzyme active sites are occupied, right? So that is referred to as the Vmax, and it's this theoretical maximum rate of the reaction. And so this is the value that our V naught, our initial reaction, is going to approach, or our reaction velocity is going to approach. And then so then it's important to also consider some of the other factors that we see on this graph over here. And so the next thing we want to think about is the rest of these factors on this graph, right? So if you think back to when we discussed myoglobin, we learned some important things when we actually looked at when the myoglobin was reached half of its saturation. And similarly with enzyme kinetics, when you reach half of the Vmax, you can sort of learn some more important things about the rate of that reaction. And so when we look at 1/2 of the Vmax, so our 50% of our reaction velocity, and we draw a line out to look at that reaction kinetic graph, and we drop a vertical line down to substrate concentration, we arrive at this constant called the Km. And the Km is defined as the concentration of substrate that is going to result in getting 1/2 of that maximum reaction rate. And similar to with myoglobin, with our Kd, right, in that case, it's going to give us an estimate of the binding strength of the enzyme to the substrate. And so essentially, if you need less substrate to get to 1/2 of that Vmax, you're going to have a higher binding strength. So, right, so low Km, it means higher binding strength of that enzyme to that substrate. And a higher Km would mean that you'd require more substrate to get to that 1/2 Vmax, meaning that maybe there is a lower binding strength of the enzyme to the substrate. Very similar to when we were thinking about our Kds and what that meant for our binding strength of our myoglobin and our hemoglobin. So what else can that tell us? So ultimately that can lead us to this equation called the Michaelis-Menten equation, or the MM equation. And this essentially is describing this graph that we see over here, this graph that has a hyperbolic shape. And so it's telling us that the reaction velocity, or V naught, is defined as this, right? So in the numerator of this equation, we have the Vmax, which is again our theoretical maximum rate of that equation. We have our concentration of substrate over here. And then in the denominator, we have the Km, which again is defined as the substrate concentration that's going to let you get to that 1/2 of Vmax. So that's one really helpful kinetic parameter that can help us learn a lot about the rate of a reaction. And there are also a number of other useful kinetic parameters that we are going to be considering as we talk more about enzyme kinetics throughout this chapter. So the first one of those is called the turnover number, or the catalytic constant. And so that's Kcat, the catalytic constant, and it's defined as the Vmax divided by the concentration, the total concentration of enzyme present. And this is essentially telling us the turnover rate per enzyme, or essentially how fast it takes for one enzyme to fully catalyze that reaction of turning substrate into product. If you want to flip that over, we can arrive at the average time for one turnover. And so we literally just take the reciprocal of the Kcat, 1 over Kcat, and that will tell us how long it takes for that one single cycle to happen, where the substrate binds to enzyme and the substrate is getting converted into the product by that enzyme. And then finally, we have another parameter called the catalytic efficiency under realistic conditions. And so this accounts for not only that theoretical velocity of that reaction, but also takes the Km, or the binding strength, into consideration. And so that's defined as Kcat divided by the Km. And so this is going to help us sort of think about, in more real life, how efficient a reaction might proceed. And so on this next slide, we have links to a few more helpful videos. These go into a lot more details about the derivations of some of these equations, and some more details about reaction kinetics overall. And so just remember that if you're interested, please watch these, but also keep in mind that you do not need to know how we derive these equations for this class. I just expect you to know how to describe enzyme kinetics, as well as how to interpret some of these graphs and parameters that we just described. So with that, now you should be ready to answer the practice questions for the Chapter 12 Reaction Kinetics section.